All right, so in this video here, we're going to talk about homework 15B. It has a lot of the little flasks on it and asks questions about the kinetic molecular theory of gases. This is the theory, this is the overarching behavior explaining relationships that tell us like what is the relationship for a gas between like temperature or number of moles, diffusion occurring, pressure, things like that. So the first, number one, part A and part B are referring to this set of flasks here. Each of these flasks is the same size and at the same temperature. Flask 1, 2, 3, and 4. Same size meaning the same volume and obviously same temperature. You know what temperature is. Which one contains the most molecules? Well, what's different about them is that this one has 1 atmosphere of pressure. This one has 4 atmospheres of pressure. This one has very high pressure compared to the other ones. This one has low pressure. What's causing the pressure? Which contains the most molecules? Because the more molecules that we pack into a container, the higher the pressure will be. So which one contains the most molecules? I'm going to say flask 4 contains the most molecules. Why? Because more pressure is caused by more moles or number of particles being packed inside. The more people you cram in a room, the more squishy it gets. Obviously, there are a lot more particles going on in here to make it 4 atmospheres of pressure, 4 times as much as that room over there. Same size room. This one's just more crammed because there's more people. In which flask will diffusion occur most slowly? So again, we're going to imagine that this room has 400 people in it. 400 people. This one only has 100 people in it. Which room are you going to be able to, which room is going to cause you to diffuse, aka walk around more slowly in? Obviously, the room that's crowded, you're not going to be able to get from this side of the room to this side of the room very fast if there's 400 people. So, which flask will diffusion occur most slowly and why? Flask 4, more crowded. I have to bump my way through more people, particles, to get where I'm going. So that's kind of how you answer these ones. I'm not going to do all of them as intense as this one. Like for this, I'll write out the answers, but the other ones, I'll just talk through them. Flask 4, because it is more crowded, more likely to have collisions in my path from one side to the other while I'm trying to diffuse and move around. The next problem, if all of the flasks are the same size, okay, same temperature, all right, and this time they contain the same number of molecules in each, then what's the difference between them? Same size, same temp, same number of people or same number of molecules in each. But this one has helium atoms in it. Helium is a very tiny particle. Let's see, it says it has the same number of molecules. So I'll draw 1, 2, 3, 4, 5. 5 heliums versus 5 kryptons. 1, 2, 3, 4, 5. They're still not touching each other because gases are far apart. They don't touch each other. But maybe that has some effect. Which flask will the molecules be moving the slowest? Flask 4. Why? Molar mass. Krypton weighs, I don't know, look at a periodic table. Krypton weighs a lot. Helium only weighs a little bit. And we know that the root mean squared velocity, is based off of the molar mass. So obviously, bigger molecules are going to move slower. In which flask will the pressure be the highest? Well, we're assuming that the pressure is actually going to be the same in all of them because they have the same volume, same temperature, same number of moles. Well, PV equals nRT. We have the same volume, same number of moles, same temperature. They're all going to have the same pressure. So same, because write me out an explanation there. Next one, each of these flasks contains the same number of gas molecules, which would be the highest pressure. Okay, so it looks like what's changing here is the temperature. We've got really hot gas over here and cool gas over here, 273 versus 400. So pressure and temperature, how are they related? And you can go back and check your notes. Are they inversely? Are they directly? But I just usually try and think it through logically. If my temperature is changing, how does my pressure respond? If I leave a bottle, an empty water bottle, plastic water bottle in my car, if it gets hot, the pressure goes up. If it gets cold in my car, the pressure goes down and it kind of crinkles instead of like is bulgy when it's hot. So they run directly related to each other. So if this one has the hotter temperature, then it's also going to have the higher pressure. Explain why. Which flask will movement occur the slowest? Well, movement and temperature go together. The cooler, the colder your sample is, less movement you'll have. So slowly is going to be happening in the cooler container. Explain why. Or just add on a little to what I said. And the last one, notice the picture here. Notice the pictures changed. We have a teeny weeny flask. Obviously, the variable that we're looking at here is the volume because this one is really, really small and this one is a rather large container. They have the same number of molecules. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Wow, which one has the lowest pressure? Obviously, flask 4. You explain why. Which container would have the highest number of moles? Well, it literally says they have the same number of molecules. So they should all have the same number of moles. Explain why. And lastly, determine if the following changes to a system will result in an increase in pressure. Will the pressure go up if, will the pressure go up if we make the volume of the container decrease? The container is getting tinier. Pressure goes up? I'd say yes. Temperature goes up, it's getting hotter and hotter and hotter, and you left the hairspray can in the car and it's an aerosol and it's like a really hot summer day and it explodes because the temperature increased the pressure. Adding more gas molecules, you squish more and more and more and pack more and more and more and more into a container. Is that increasing the pressure? Yes, it's more squishy when you add more people. If you increase the volume of the container, you had 5 or let's do 6 people in a room, but now you have a bigger room. Did that make the pressure go up? No, it's the opposite of this one, right? These two are opposites. If decreasing the volume increases the pressure, then this is the opposite. So this is kind of the summary for how the variables come together. Volume, pressure, temperature, pressure, number of particles and pressure, and then obviously ask yourself, do you know the relationships between the other ones? What if I asked you about the volume and the temperature? What if I asked you about those? What if I asked you these same questions, but I asked you what happens to the volume if we change the number of particles, right? So that's what's on the top of notes 15 on the back side, is just those relationships again. You can usually think through them pretty logically. Like I always just think of an empty water bottle, plastic water bottle in the car. That seems to help me because I can think through it. Like if the temperature goes up in the summer, the bottle gets like really fat looking. And in the winter, it like crumples. So it's a good example for temperature, how pressurized it is, the actual volume size that it's trying to change to. So there you go. There is homework 15.